Great, hello everyone. Welcome back to 418-618. Today we're going to be talking about certainly the midterm exam. We'll do that first. And then we'll begin our discussion of structured perceptron and structured SVM, which are going to be our examples of how we can actually use map inference as a subroutine in learning. And we'll see exactly how far we get. I think we may very well get through both. So that's the plan. So the exam is on Thursday at 6:30 p.m. So I'll see you all there. And homework 3, as we had mentioned before, isn't going to. Oh, that's not even there. This is completely out of date. Anyway, the point is, homework 3 is going to be released after the midterm exam. So we'll send that out probably over the weekend. Okay, so a couple just logistics. The time and date I already mentioned. The room is Hamburg Hall, A301. Does anybody know where Hamburg Hall is?
No.
It's a genuine question. I don't either. Yeah.
It's by the, you know where the supercomputer is?
Also,
No.
Okay, so from Gates you can get out in the loop that goes out towards Forbes.
Uh-huh.
The building that's across that way is Hamburg Hall.
oh, okay, okay.
So CIC is the building that's on the left if you go follow the loop, but if you go straight across rather than following the loop around, the building that's past the cul-de-sac there, that's Hamburg Hall.
Okay, good. Thanks for letting us know. And so there will be assigned seats. So if you just arrive a couple minutes early, that'll help us sort things out. Though we'll make sure you get your full 90 minutes if it takes us a few minutes just to find everybody's seat. And we'll announce any more. If there are any other logistical details, we'll use Piazza to announce them. But I think this is mostly it. So I already mentioned that the material covered is lecture 1 through 13. So this is everything up to and including map inference. And then, the types of questions should look kind of familiar. They're mostly of the variety that appeared on the homework. So, some multiple choice, some true false, sort of very short derivation type questions, short answers in, say, plain English, interpreting figures, also drawing figures, maybe implementing algorithms on paper. And you won't need an electronic device, so you shouldn't bring a calculator. You don't need it. But you are allowed to bring one 8.5 by 11 sheet of notes, front and back. I always remind people here that there's no research supporting the notion that having such a sheet of notes will actually improve your performance on the exam, but it will actually make you less stressed while you're there. I tend to think that just this process of actually creating the thing is actually incredibly valuable. So just this notion of you going through and trying to distill down all of the things that you have learned into a small space is actually a really valuable exercise. So kind of all of the usual exam advice applies. Don't leave anything blank, solve the easy problems first. If you make an assumption, just write it down. If you look at a question and don't know the answer, they probably haven't told you, but you could probably figure it out. I think the main one of these is, if you make an assumption, write it down. So as you've seen, there's lots of cases already where we've written say homework problems where we didn't clearly enough state our own assumptions. And so we're trying to be more and more precise about this, but if you notice a question where something seems like under-specified to you, that's fine, just raise your hand, ask a question. We might clarify it in the moment, or you can just sort of write down an assumption that seems appropriate to you. Okay, so we've already talked about a lot of things, so well up. So this is sort of the content that will appear on the exam. So, we've talked about search-based structured prediction. This is where we started. And we used reductions to binary classification as sort of our jumping off point to get around to this notion of just generally reducing one problem to another. And from there, we saw how we could take a problem and recast a structured prediction problem and recast it as a search problem, and then how learning could be reduced to training a classifier on that search problem. And then, we essentially from there looked at some very, very fancy classifiers, sort of things like RNNLMs and seek-to-seek models, where the entire representation of the state in your search space so far might be reused from time step to time step. So this whole notion of decomposing a structured prediction problem into a sequence of steps, it was only sort of one way of decomposing a problem. And so the next way we looked at it, decomposing a problem, was graphical models. And so we contrasted a couple different representations. We looked at directed graphical models, undirected graphical models, and factor graphs. And those are just visual, they're essentially visual notation for representing a set of conditional independencies that hold between a collection of random variables. So then we talked about Bayesian networks, Markov random fields, and conditional random fields, which have a rough correspondence to some of these visual notations, but fundamentally the models in this list, Bayesian MRFs, CRFs, are just models, and you can have one even if you don't have the visual notation representing it. And we also saw that some of the visual notations, like factor graphs, are capable of representing all of these kinds of models. So from there, we actually said, all right, well, this is great, but we actually want to learn the parameters of these kinds of things. And so here we thought, well, just to kind of keep learning sort of in its simplest possible form, we restricted our attention to fully supervised learning, right, where we observe all of the variables present in the graphical model. Okay? And so, this gave rise to our discussion of fully observed Bayesian network learning, fully observed MRF and CRF learning, which were gradient-based, whereas the BayesNet learning we saw was count-based. And further, we saw that, in order to even talk about learning, you need to have some notion of how your network is actually parameterized. What is the mapping from parameters to actual scoring functions or potential functions. And I think of note, we've been looking at this particular case where we have neural potential functions. And what this allows us to do is kind of get the best of both worlds from both deep learning and graphical models. And so the last thing that we looked at was exact inference. And here we thought about these three inference problems: computing marginal probabilities, computing the partition function, and computing the most probable assignment, or map inference. And we looked at variable elimination and belief propagation in the sum product case for computing for solving the first two of those inference problems. And then we saw that the max product BP algorithm and map inference via mixed integer linear program could handle the third inference problem, finding the most probable assignment. So at this point, next we're going to look at some sample questions, so we'll get there. But at this moment, I think it's actually good for us to pause and to look forward a little bit to to what it is that's coming after this, sort of what are the parts of the story that we really haven't yet told. And fundamentally, the main part of the story that's missing here is, so I guess maybe I'll highlight a couple points. So one is that we've only sort of scratched the surface on search-based structured prediction. There's a lot more algorithms that we could talk about in that space. But I think that we've kind of hit on sort of the most fundamental of them. In the graphical model space, this restriction to, and so I guess I should say a couple more things on search-based structured prediction. So specifically, we also, in that setting, we're sort of assuming that, for example, the Oracle policy that we had access to was actually optimal. But there are other imitation learning settings where you might not have an oracle that is exactly or that is known to be the best you can possibly do. So think about an example like ad placement. So this is like a multi-billion dollar industry, and the way that people often place ads is some combination of sort of machine learning rules and handwritten rules, because the handwritten rules actually determine part of the decision process, which is where do you actually want to put these things on the page. Okay. So if you have a rule-based handwritten notion of how to place ads on a page, that gives you some notion of a probably non-optimal oracle. Maybe we shouldn't even call it an oracle, you could just call it a teacher at that point. And so you could imagine a slightly different learning setting where you're trying to learn from some teacher, but you actually want to do better than the teacher is doing. So this is an example where we could go beyond sort of what we've seen in search-based structured prediction. So in graphical model learning, we've restricted to this fully observed case, but I think that a lot of the power of graphical models comes about when you're in a low resource setting. So you're doing either unsupervised learning or semi-supervised learning, or you have, so those two usually capture sort of the simplest possible cases of partial supervision. But once we have sort of described a setting in which we observe some variables and don't observe others, now there's lots of different ways that we can talk about partial supervision that don't necessarily fit into the paradigm of standard semi-supervised learning, with some examples labeled and some unlabeled. So that's an incredibly important thing to start thinking about, is how those learning settings will evolve. And then in the context of inference, we've seen that, okay, there exist algorithms like variable elimination and sort of a mixed integer linear programming solution to map inference that can solve these problems for arbitrary graphical models. Okay, but we didn't say that they were going to be fast. Okay, and so in practice, most of the time when you're using an interesting graphical model, we're not using exact inference. We're going to have to resort to methods for approximate inference. And so those methods will include sampling methods. They'll include things kind of like relaxations of integer linear programming, like dual decomposition. They'll include a broader class of methods called variational methods, of which belief propagation happens to be an example, but we'll delve a lot more into what variational inference actually looks like. And as well, there's sort of this collection of deep generative models that have become really popular recently that have their roots in variational inference. So we'll also look at this case of variational autoencoders coming from the perspective of how inference is actually carried out in these sorts of models. Okay, So that's a lot of both what we've done and also where we're going. Okay, let's look at some sample questions. Okay, so suppose you're training a seat-to-seat model for supervised POS tagging. And let's say that the inputs to your encoder are E1, E2, E3, and so on. And then your inputs to your decoder, maybe we should be drawing a little picture as we go here. So here's your encoder. And here's your decoder. This is how I would be solving this problem if it were given to me. So here's E1, E2, E3, and then decoder has inputs D1, D2, D3, and outputs O1, O2, O3, and so on. And so here we're just asking, describe in words what the inputs to the encoder will be, assuming you're training with teacher forcing. And here, the task that we're working on is, say, supervised POS tagging. Part of speech tagging. Great. So what would the inputs to the encoder be? Yeah, they might be embeddings of the actual words that we're feeding in. They might be a one-hot vector representation of the words, or just generally some feature representation of the word. But one for, so the, ET is going to correspond to the tth word in the sentence. Okay, so then what are in English, what are the inputs of the decoder? So here, I assume you're using teacher forcing. Say it a little louder. Yeah, so let's be a little bit careful here. So why don't we actually answer this one first? So you're right that they're going to be the ground truth POS tags. But let's get specific about what the outputs of the decoder would be. So what are the outputs? Say, what is OT? Yeah, it's a probability distribution over the POS tags for the tth word. Okay. All right, great. So here, what is, say, DT? So we said that ET is some representation of tth word, and OT is a distribution over tags for tth word, and DT would be what? Is it a representation of the tth tag? Yeah, so it would need to be some representation of the t minus first tag, right? So we would feed in some start symbol for D1. So we would say D1 is some start symbol, and then DT is going to be, so say D2 here would be the representation of the first ground truth tag, and I guess we would need to be careful here to say ground truth. So, okay, so great. So here's 3 more questions. They're the same questions, except that now we're assuming that we're using scheduled sampling instead of teacher forcing. Okay, and if you want, if your answer is the same as for teacher forcing, you can just say write the same. So what would we have for the first one, which is describing what the inputs to the encoder would be? Same, right? Okay, and then question 5, describe what are the inputs of the decoder.
The previous distribution will take the argmax and that range.
Yeah.
Feature representation.
So we could say that, oops, dt would just be a representation of the t minus first predicted tag, as opposed to the ground truth tag. Okay, and what would the outputs of the decoder be? The same. Okay. Okay, so so here's another problem, and it seems to be okay. So somehow I think there are fonts that exist on a Mac that, when copy pasting snippets of PDFs into my PowerPoints, they're getting lost in the translation to Windows. Okay, so this is why I'm not noticing these things until I actually project them here. So I'll have to come up with some solution. So the things that are missing are just assume that the factors are named psi A, psi AB, psi ABC, and psi C. And so we have this factor graph, and there's 3 binary random variables, A, B, C. Okay, so using the given factor names, we want to write the partition function z that ensures that the joint probability distribution P of ABC sums to 1. So how would we write this partition function?
It would just be the sum over all the values of A, B, and C, of psi of A times psi of AB times psi of ABC times psi of C.
Right, so we'd have psi of A, psi of AB, psi of ABC, and psi of C. And crucially, we have to sum over all of these, and since they're all binary valued, these are just summing over the sets 0, 1. Okay. So here, using the given factor names, write the joint probability mass function defined by the factor graph shown in figure 4. Okay, so I think you guys all know how to do that one, and here maybe we even said you could include the term z directly in your answer, right? Okay, so now suppose that you have a joint probability distribution that factors as below. So here, this is a new distribution with factors like the ones shown. Okay, and here, what we have is that the probability is proportional to the product of these factors. And so now we're asking you to actually draw the factor graph corresponding to this factorized joint distribution. Okay. So, what would the factor graph look like? Actually, why don't you take 30 seconds and jot down what the factor graph would look like and then describe it to me.
I have a question with the scheduled sampling.
Oh, sure.
Is it only, do we only choose the previous, like the 017 tag, 017 tag when we're with some probability
probability when we're doing dagger. So the schedules have more than 100%, are previously predicted tag.
So part of the reason that we called it scheduled sampling is because you need some schedule of how to, over time, change the mixture of the Oracle policy and the models policy. So this question is a great one where like we didn't state our assumptions, right? So we didn't actually say, you know, what is that mixture here? So if we had just said predicted tag, I'm actually making the assumption, I guess, that the mixture is 100% model.
Okay.
So hopefully on a question like this, we would have specified what the actual mixture distribution is.
So it wouldn't be wrong to say like the representation of the T-1 predicted tag with some probability.
Yep, that would be great. That would be a much better answer than what I wrote here. So if we had said, yeah, predicted tag with probability, you know, beta t and ground truth. I like this answer better with probability 1 minus beta t or something like that. That would be great. Okay. Okay, so here, did anybody, while we were talking there, actually already come up with this thing? You guys are still thinking. Okay, wait a minute. Fix your font, it's really something small. I gotta keep forgetting that. Thanks. Okay, does anybody have an answer here? Yeah.
Yeah, I don't know how to describe this, but
Why don't you describe, okay, so are there gonna be some circles?
there's, yeah, you have each of your nodes,
Okay,
so
so
there's a
what are
unary
they?
factor coming off of X.
Okay, so a unary factor off of x, great. Are there,
An edge factor between X and Y.
okay, great,
I just called it a clique factor between X, Y, and Z.
okay,
And you have an edge coming between Z and W. And an edge between Y and W.
great. Okay, so basically we're just,
Y and Z, right?
oh. Okay, does everybody agree with that? Yeah, so what we're looking at then is just some factor representation of the actual factors themselves, right? Okay, so so here this is a lovely little question. So suppose you have yet another factor graph where we actually have the factors shown. Now draw a table containing all of the values of a scoring function of S of QR, which is the product of those two factors. So you could imagine filling in a table that multiplies these two factors together. So here, then we ask, okay, what is the value of the actual partition function, z, for the joint distribution? Okay, so imagine you've just created this table, SQR. How would you compute the partition function from it? Yeah, just so if the table looked like, you know, like this little factor table up here. So you have the different values of QR and then you have S of QR. So if you built out such a table like this, then you could just take the sum of all the scores here and that would equal Z. So that would give you the partition function. Okay, so then here this is just asking what's the joint probability of a particular assignment of the variables? How would you compute that?
Do like 1 over Z times like their respective.
Yeah, so if you already computed this table, just take the entry in that table corresponding to, let's see, what was it asking for? Q equals green, R equals crayon, and I just pick that score out and then divide it by Z, and there's your probability. Okay, so then this is asking what's the marginal probability, P of Q equals green, and here you could just add up the probabilities of all of the probabilities for which Q is equal to green, summing over the different values of R. Okay. So now suppose you run the variable elimination algorithm to eliminate variable Q, resulting in a new factor graph with just one factor MR. Okay, so you could then draw a table containing the values of this factor. So what would that new factor table actually look like? How many entries would it have? Yeah, just 2 for pencil and crayon. And how would you get the entries in it? It's going to be some table like this. Pencil, crayon. And what would the value here be? Yeah.
Some scoring function with all Q values.
Exactly. So if we already computed those scores, we'd just take the score of red pencil plus the score of green pencil plus the score of blue pencil. Great. Okay. And there's another marginal probability question. Okay, so now suppose you're running the variable elimination algorithm on this factor graph, and the first variable you eliminate is B. So draw the factor graph that results after you have eliminated B. So what would that look like? Let's give someone else a chance actually here. Someone new.
Instead of the B circle and the factors that are attached to it, you'll have an NP, and it will be connected to A and C.
Yeah, so we're going to keep these unary factors, right? And we're just going to have some new factor that touches both. Great. Okay. And this is maybe what we would call like M sub B for the factor that we got after eliminating B. Okay. So now suppose you're running the belief propagation algorithm. How many messages are required to send a message from the factor f ABC to the variable C? Yeah, 2. We need this message and this message in order to send that message from factor to variable. Okay. Okay, so another question would be, is there a Bayesian network? Oh, question?
So like for that question, what if you like interpret it as like you need all of the like messages. So you need to send a message from like A to B as well. So like you would get to assume that you just did one.
Yeah, so this isn't a good question. Yeah. Well, I wrote this in like the couple minutes before class. This has never been used anywhere. But yeah, this would be a bad question. There's a lot of reasons that it's bad. One would be that we probably wouldn't ask you to run belief propagation on a loopy graph because we haven't talked about loopy belief propagation yet. And then 2 would be, yeah, there's kind of this ambiguity, which is like, yeah, are we talking about just the 2 incoming messages? Or yeah, is there some notion of other messages? So anyway, in this particular case, if we made the graph acyclic, then there might be sort of 2 unambiguous answers here. One being the two coming in and one being all the messages from some subgraph. Yeah, great question. Okay, so I think this is a good question. Let's see. Is there a Bayesian network that would convert to the factor graph shown above? So assume that, like the question is basically, does there exist some Bayesian network such that when converted to a factor graph would yield this? So if yes, draw an example of such a Bayesian network. If not, explain why not. So let's do a quick show of hands. How many of you would say, yes, there is such a Bayesian network, and how many of you would say, no, there's not? Okay, so how many for yes? How many for no? Okay, and then how many for still working on it? Okay. How many for I'm not actually working on it? Because there's some people that didn't raise their hand. Okay, so you should have a good prior here, which is, it's probably going to require you to draw a Bayesian network just because it feels like a better question that way. Okay, so the answer is yes, I think. I think I found one. Does anybody else think that they found one that works here? Yeah?
So maybe like A would be the root node,
Okay.
and it will have B and C, but C will also have a parent as B.
Like this? Yeah, so if you remember how the factors of it, so I think in some sense it's actually a little bit easier to go from the Bayesian network to the factor graph than to go from the factor graph to the Bayesian network. So the key thing to remember is that in a Bayesian network, the things that we are multiplying together are one term for each variable, where that term is the probability of that variable conditioned on its parent. So that would be P of A times P of B given A times P of C given BA. And if we were then to convert these to factors, they would look like F of A, or if we were to just rename them as factors, they would be like F of A and B and F of A and B and C. Okay. So that's how we got there. And these are the factors corresponding to that picture. Okay, any other questions? Yeah.
Is there like way to know if a factor graph does not have a Bayesian network?
Oh, good question. So you'll notice. So let me delay my answer a little bit because the real answer is I don't know. But one thing that I'll observe here is that I did not include. So the previous example here had a unary factor on C. Okay. So I had to remove it here because in order to make this work, I needed only the root variables to, so in a Bayes net, there can be multiple roots, right? So a root is just a node that doesn't have any parents. And so in a Bayes net, all of the root nodes are going to have unary factors on them. And there wasn't a way for me to get back a Bayes net that had both A and C as root nodes with this particular set of other factors. So so the reason is basically like, there was only one possible child, B, for both of those roots, and yet there were two factors for it. So those two, so in this case, I mean, one way that we could say that there does not exist a Bayes net for this particular graph is that there's just too many factors. We know that there should be as many factors as there are variables, right? One for each variable conditioning on its parents. So if the factor graph has more factors than there are variables, then it can't possibly be that this would be sort of the correct factor graph represented. So whether we can do that more generally, I just haven't thought it through ever. So.
But then can't you just add f of c to that factor graph? Because I thought you could convert any like Bayes net or whatever into a factor graph and back, right? Like you can have more potentials than there are nodes.
So we can always have more factors in a factor graph than there are nodes, but I guess we described sort of one specific way of, so let me be careful about my statement from before. So possibly what we could do here is we could say that, let me see if I can do some gymnastics to make this work. So with this new factor graph, we could say there's a Bayes net that looks like this. Okay, where we define P of A, or sorry, F of A is equal to P of A, F of C is equal to P of C. And so here's the odd part, right? So I can go the other direction and I could say something like P of B given A and C, we could actually define as the product of FAB times F of ABC. So long as this was a properly normalized distribution. But it feels weird to go in the other direction. So so in the particular way we set things up in this class, there was a specific way of going from a Bayes net to a factor graph, one factor per variable. And so while I could potentially, so basically like a different question would be, does there exist a Bayes net that encodes the same conditional independence assumptions as this factor graph? And in that case, I would say the answer is yes. It's this one.
I'm not sure about this, but when I was reading one of the reading material in Jordan,
Yep.
so I think he was creating like new nodes, and for any factor graph, he was able to make a Bayes net by creating all these new nodes.
Oh,
But I'm not sure about this.
for any undirected?
For any directed.
No. So did he go from undirected graphical model to Bayes net, or did he go from factor graph to Bayes net? Just out of.
One of those.
So I would guess that he went from undirected to directed, and so I guess what I'm trying to get at here is just that this particular question is constrained by the fact that we said, is there a Bayes net that would convert to this factor graph? If you were just doing sort of the standard conversion of Bayes net to factor graph, and so that is a different question than can you encode the same set of conditional independence assumptions between two factor graphs. Yeah.
So should we be able to determine conditional independences from a factor graph?
Oh, good question. Should you be able to? Yes. So I think like right now we have like two such questions that I can think of on the exam, and it's free. You get that for free. Surprise. And I think they're like very simple. So what I don't want you all to do is spend the entire week, trying to deeply understand how to perfectly perform every possible notion of d-separation in any factor graph ever given. That's more of like a homework style question. If you can get like if you can remember the very basics of d-separation to perform them on a tiny graph, that's sort of all we'd be looking for.
But like, would it make more sense to like convert this into like a Bayesian network and then like apply those rules, or should we be able to like from this information like be able to like figure out the conditional?
Oh, I see what you mean. So I think I guess we didn't spend a whole lot of time talking about conditional independence assumptions on factor graphs. We mostly we talked about them not in terms of d-separation, but in terms of say Markov blankets and then sort of the general separation property of undirected models. So usually, basically, like the main thing that I think is like just moderately tricky is sort of d-separation on a Bayes net. And then the other properties like Markov blankets and separation on undirected and factor graphs are kind of easy. They're just kind of like visual inspection. Other questions? Yeah.
So when you're comparing the conditional independences of two graphs, don't you have to look at all the positions?
Yes, you would. That's why I asked the question this way, right? So this way, it's like we're avoiding the need to enumerate every possible conditional independence assumption for each graph. Again, it's a great homework problem where you actually have to kind of think through every possible one, but we probably wouldn't ask you to do some long enumeration like that on an exam. Though I guess I shouldn't rule that out. But anything is fair game. But that seems like the type of question that we would steer away from.
So does it mean every factor graph will have one Bayesian net and vice versa?
So I mean, we just established that essentially, when adding this additional factor, we said there's no Bayesian network that, if you just sort of follow the standard way of converting a Bayes net to a factor graph, would yield this one.
I think that rule more generally is like you can't have two parent nodes connected to each other. So like A is like a root node, and C is also like a parent. So like a parent, or like that technically shouldn't have a parent because it has like its own marginal probability, but it does have a parent. It's connected to.
Yeah, although if we got rid of FAB, then we're fine, right?
Yeah.
So in that case, there's still.
Well, no. If you get rid of AB, then you have F. You still have AC, right? Like A and C are still connected. But C having a marginal probability means that it should be A.
Yeah, it would have to be a. Yep, that's right. But it could still participate in other factors so long as it's
Just not connected to A.
Yes, that's right. Oh, yes. So that would be another rule to rule out. Okay. Great. Okay, so this is why I did not promise to get through both structured perceptron and SVM today, because I wasn't quite sure how long we would end up spending on this, but this was time well spent. And so what I want to do now is move into our first look at structured perceptron. And yeah, we'll get through it. So just a reminder that what we did last time was we said, okay, if you have this, MRF, you could, or in this case CRF, you could rewrite it as a integer linear program where we now have these indicator variables that are telling us whether or not a variable is taking a specific value. We did an even more compact representation sort of in our notes where we had one variable just saying, is this variable equal to 1 or not? or just taking on the value of the variable 0 and 1. So this allowed us to then write down this map inference problem as an integer linear program. And so now what we want to do is think about how can we use that map inference program inside the structured perceptron learning algorithm. Okay, so to do that, we're going to start by just sort of doing a quick refresher on linear models. So here, our setting is that we're going to assume that we have training examples, which are XY pairs, okay, where we're going to say that X is some vector, say of length M, and Y is some integer from 1 up to K. Okay. And so our model, for just sort of a standard linear model, is going to have parameters, which we'll call theta. Oh, actually, sorry, let me make a small change here. I had this change in my note, I just wasn't looking ahead. So X is actually going to be a vector of length P here, and the parameter vector is going to be of length M. So, in addition to parameters, we're going to assume that we have some feature function. And that feature function is going to be some f of x and y that returns a vector of length m. Okay. So, to make a prediction, we just return some y hat. This is our decision function, h theta of x, which is the argmax over all possible y's in the set 1 up to k of theta transpose f of x and y. So, okay, so let's just think about a couple examples of these feature functions, because it's useful to see just how general this setting is. So one such example would be, so this will be example 1. We're going to say that here f of the vector x and y is defined as follows. We're going to make a big matrix, and that matrix is going to have a bunch of rows, most of which are just filled with zeros. But then in the middle, there's going to be a row somewhere that contains the vector x, x1, x2, up to xp. And so this matrix, we'll say, is a k by p matrix. And it's defined so that only the y'th row is non-zero. So you can imagine having these rows numbered, and it'll be like row 1, 2, y, up to k minus 1, k. Y is the current class that we're constructing this feature vector for. Okay, now I promised a vector here, so
what we're going to do is wrap this entire matrix in a function called vectorize, okay, which is just going to take this matrix and stretch it out into a long vector-looking thing like that.
So this vectorize is just going to stretch this out, and that would mean that the value m is just equal to k times p. So the number of parameters we have is equal to the number of classes times the length of that vector.
Okay, so this is cute, but honestly, it didn't really accomplish anything interesting.
All it did was we just took, kind of the usual way of representing a linear model. So it's like we could have just had theta be some matrix, and then we could have said we're going to take theta sub y, the y'th row of theta, and we'll take its dot product with x.
Okay, so let's look at another example. So this will be example number 2, where now we're going to suppose that the labels 1 up to k exist in some hierarchy. Okay. And also, we're going to continue assuming x is a length p vector, but now we're going to say that it's a binary vector of length p. Okay. So what would a hierarchy look like? Well, maybe it's something like we have some root node, and then we have at the first level something like mammal, reptile, and amphibian. And then under mammal we have both cat and dog, and we could say under reptile we have turtle and snake, and under amphibian we have frog and salamander.
So here's some hierarchy, and
so how does this map to 1 to k? Well, each of these leaf nodes has some label, right? So we could say, this is label 1, 2, 3, 4, 5, 6. So here k is equal to 6. Okay. And then we could define our feature function. So this is now our f of x and y to be something like a collection of binary values where the first one might be an indicator saying whether or not x1 is equal to 1, since x1 is binary, and y is, say, in the subtree mammal. And then we could have another indicator that's something like x1 equals 1 and y equals cat. So that's actually a little more specialized. We could do the same thing for x1 equals 1 and y equals dog. Okay. And we could kind of keep working our way down, and we would have lots of other indicator features, like maybe we have xp equals 1 and y comes from the amphibian subtree. And many more features after that.
so here, what we're doing is we're basically saying we could actually take some structured information that we have about y and encode it
in our features such that now we actually have more interesting parameters than we did before, right? So, for example, the original linear model setup that I did before, it would have a parameter for each of these cases, right? Where the x1 feature was 1 and y was equal to dog. There would be some feature that would be added into the dot product in example number 1 for that case. But the new one, the interesting one that we added here, is this first case, which is sort of like a back-off feature that's basically allowing us to capture some interesting notion of the fact that, we're a little bit unsure. We're not exactly sure, or we don't even care whether y is cat or dog. There's some really useful information encoded just for the case that y is a mammal that's sort of shared for both cats and dogs. And so you could imagine if you were regularizing a linear model like this, it would be useful to have these sorts of back-off features because you might be able to get more out of the actual classifier this way. Okay, so what we're talking about here isn't going to be restricted to linear models. In fact, what we're doing here can be applied to sort of much more complicated models, but it's useful to kind of have these in mind as a starting point. There's another example of a linear model just like this that already came up in this class. Does anyone of you remember it? Homework 1. So you guys have actually seen multi-class perceptron before. It showed up sort of by accident on homework 1, where we had set up a particular problem one way as a binary classification problem, and then we switched over the feature function to be a function of x and y, and broke our ability to use standard old binary perceptron. Okay, so here's the key idea of multi-class perceptron. If the prediction is incorrect, so that would mean that y hat does not equal the true y, then the idea of this is that we're going to increase the score of y and decrease the score of y hat. Okay, so what does the algorithm actually look like? So we're going to say that we have some initial parameters, call them theta, that we set to 0. And while we have not converged, we're going to say for each xy in dataset D, we're going to compute y hat to be the argmax over the possible values of y, which are going to be k from the set 1 up to, say, capital K here. Let's just use j, so it's really clear. So here this is the jth class. And then we're going to compute theta transpose f of x in class j. Now, if we make a mistake, meaning if y hat does not equal the true y, then we're going to make an update to the parameters. And our update should be such that we increase the score of y and we decrease the score of y hat. Okay, and then at the end, when you've converged, you can return theta. Okay, so this is a nice little algorithm. And so now we want to ask the question, how does this all fit in with structured prediction? So for one, the algorithm that we just set up is actually both the multi-class perceptron algorithm and also the structured perceptron algorithm. So here, this algorithm is the same as multi-class perceptron, with each possible output structure, right? Each possible y from the set y of x as a class. So, I mean, I put class in quotes here because basically what we're saying is you could imagine enumerating every possible structure that exists. Okay. And you could imagine then encoding each of those structures as a class. So let's think about what the training examples actually look like, and then let's think about what that encoding might look like. So training examples are again XY pairs, where the vector x is again RP, and the vector y is, say, RT. And as before, we have some feature function which takes an x and a y and returns a scale. Oh, sorry, a vector of length m. So essentially, what we're doing is we're saying, so if you like this notion of a vector embedding, we're saying come up with some function that you decide yourself, call it f, that takes an x and a y and gives you back a vector representation of that xy pair. And then we're going to make predictions as y hat equals argmax. Oh, and let me be, sorry, a little more pedantic. So instead of saying that y is in RT here, let's just say that y comes from some set y of x. And if we want to, we could call this vector x some set calligraphic x. And this is fine, we're just sort of using it to denote, actually let me do that the other way around here. So let's go ahead and say that x is from the set calligraphic x, but in practice this is probably just some feature vector of length. But the exact specification of what x is doesn't even really matter. Right? What we care about is that the
feature function returns a vector of length m.
And so we could say that we kind of think of this as some representation of the pair x, y.
So to make a prediction, we return the y hat, which is the arg max y hat from the set yx. That gives us the highest score, theta transpose f of x and y. Here this is y hat. So this is just a linear model where we've encoded things as a feature vector.
The calligraphic y(x) could be could be a bunch of trees or any kind of structure, right? So now our prediction has to be a tree if there is any kind.
Yeah, so this is, so we could have, the set of all trees or the set of all Wikipedia info box completions. Right, or the set of all semantic segmentations of an image. So in general, the best way to kind of think about this setting is just one where we're kind of using a conditional random field, right? So it would be totally natural to have sort of any collection of random variables that you might use in a conditional random field here.
Okay, so the last detail is the actual algorithm for structured perceptron is exactly the same as that for the multi-class case. The only difference is in this line where we're computing y hat, we should just rewrite it as y hat gets the argmax over all y hats in, this is the prediction step that we just wrote, in y of x of theta transpose f of x and y hat.
So this is the structured perceptron algorithm. And all these other lines are exactly the same, except for this one that we changed. So what we're doing in this structured perceptron algorithm is essentially increasing the score of the true y and decreasing the score of the predicted y.
Okay, so the remaining question is, how on earth do we compute this thing?
Well, if you think about it, this is basically just, say, the numerator of a log linear CRF. And so if f of x and y decomposes according, or sorry, let me write it another way. If this dot product decomposes according to some factor graph, then solve this essentially map inference problem. With an MILP.
So the last detail here. Right, so basically, if you define your f based on a factor graph, great, then you've already ensured that that it decomposes in this way. And so one way that you could actually ensure that, just as an example, would be you could define theta transpose f of x and y could be defined as a sum over all possible factors or cliques c, and for each one you're adding up theta c transpose fc of x and some subvector yc, where these are the variables in, say, clique or factor c. So this is one way of ensuring that that you get the decomposition that would work out efficiently. Okay. So the last detail is that just as the standard perceptron algorithm has a mistake bound, we also get a mistake bound for structured perceptron. And the resulting theorem is fairly similar. So it says for any training sequence, so if you imagine examples coming along one at a time, which is separable with margin delta, then the perceptron algorithm, the number of total mistakes that it makes, is going to be bounded by r squared over delta squared. And here, r is just a constant that looks at not the, so in the standard perceptron algorithm, r is the largest L2 norm of any vector x in your data. And here, r is just the largest of any difference between a pair of feature vectors. So what's interesting is, if you think about this difference, this is what we're bounding by r, right? And if you jump back to the algorithm, that difference is exactly this f of x minus y minus f of x and y hat, what we're taking here. So the fact that sort of in the standard perceptron algorithm we would be adding in or subtracting the feature vector here, whereas now we're taking this difference, is exactly why we ended up with r being the same way there. Yeah.
Is it the norm of that?
Yeah, sorry, these bars are, this is an L2 norm. Yep. Okay, so the last detail, since I already kept you late, I'll take you one more minute. So the results from this sort of landmark paper in 2002 were for these two tagging problems. And basically the finding was just that you could do the structured perceptron on these tasks and outperform a sort of now antiquated maximum entropy Markov model. But the reason that I put this slide up is that there was this trick, which was to actually average the parameters that you see during training. And this averaging trick is actually really important to sort of successful use of this structured perceptron model. And it ties back just to the standard averaged perceptron model. Okay, so we'll leave it there and pick up next time with structured SVM. See you then.